Hello, my name is Allison Moore, and I'm an assistant professor at Virginia Commonwealth University. Thanks so much to the organizers of this seminar on classical knots and virtual knots at The Ohio State University. What I want to tell everybody about today is a project that I've been working on with my collaborators, Eugene Gorski, Ty Lidman, and Bebe Liu. What we've been thinking about are Milnor's higher order linking invariants, especially the triple linking number, and trying to determine where these numbers show up in the link Floer complex and what they mean. So thanks so much for having me here. I hope you enjoy hearing about some parts of this project. So let's start by talking about algebraically split links. I'm going to be considering links in the 3-sphere, and algebraically split means that pairwise all of the linking numbers are 0. A great example of that is the Whitehead link that we see pictured here. The Whitehead link holds a really special place in art and history. You can see it here emblemized on Thor's hammer, a drawing of Thor's hammer from a book from 1906 by Montelius about the cultural history of Sweden. And it shows up in all sorts of different places. It's a classic linking number 0 link. Another favorite and really well-known example of an algebraically split link are the Brunnian rings. Everybody's probably seen these rings. You have 3 circles linked together, and if you take one away, the other 2 fall apart. So it's not just that it's algebraically split, but that the sublinks are unlinks. Brunnian rings get their name from the Borromeo family, which is an aristocratic family from Italy. And you can see the Brunnian rings all over the islands that they still own today. But you have to look carefully because sometimes they're not actually Brunnian rings. There'll be small errors, so perhaps 2 of the components are a Hopf link. This is the Borromean snakes. This is not actually in Italy, but it is a castle in northern Wales. I'm fond of that one. And here's an example of molecular Borromean rings. This is due to the Stoddart group. You can read about it on Wikipedia. It's very fascinating that the Borromean rings have actually been synthesized at the molecular level. And finally, one more image. This is just to demonstrate that you have to be a bit careful. This is a lovely Art Nouveau print by the artist Mucha. And at first glance, it looks like the Borromean rings. But if you investigate, these are all actually mutually linking number 1. The sublinks are Hopf links. So when you look for Borromean rings in the wild, you have to be a bit careful. Since we've been discussing algebraically split links, we've seen the linking number. So let's now discuss some higher order linking numbers. And the first one that I want to talk about is the Sodal-Levine invariant. Let's let L be our algebraically split link. And let's let F be the Seifert surface for link component L. The algebraically split condition guarantees for us that if we take the intersection of the first link component and the second Seifert surface, it's empty. And likewise, if we take the intersection of the second link component and the first Seifert surface, it's going to be empty. So let's let L12 denote the curve of intersection that comes from intersecting F1 and F2. Let me draw an example of these surfaces and curves using the Whitehead link. The Whitehead link has 2 components pictured in blue and red. So let's use blue and draw in the Seifert surface for the blue component. This is an unknot, so we have a disk, but it shouldn't intersect the red component, so we need to tube around one of these arcs. This will be our surface F1 for L1. This will be link component L2, so let's now draw surface F2. And let's use pink for that. So here, what we're going to draw is an annulus. And then when we get to the clasp, we're going to add a twisted bridge here, going over. So as it turns out, both of these surfaces that I'm drawing are punctured tori. And now the pink surface and the blue surface are going to intersect. I'll draw the curve of intersection in the third picture just so it doesn't get too crowded. But that curve of intersection ought to look something like this, where it picks up a twist when it goes around the clasp. So in purple here we have L12. And here we had F2. With this, we can now define the Sodal-Levine invariant. Let's make the Sodal-Levine invariant beta, and that is the linking number of L12 and a push-off of L12. And you can push off with respect to either F1 or F2, and it won't change the answer. What we're seeing here is one way of defining the Sodal-Levine invariant. It can also be defined using a Thom-Pontryagin construction. And we're seeing here a kind of intersection theory variation of the Sodal-Levine invariant. A good place to read more about this perspective is Cochrane's Memoirs of the AMS from 1990. Milnor invariants can be thought of as arising this way as well. Let's say a couple words about Milnor's higher order linking invariants in general. So roughly speaking, the Milnor numbers, mu I, or sometimes they're called mu bar with indexing I, measure how deep the longitudes of the link lie in the lower central series of pi1 of the link complement. So I have written here the start of the lower central series. And what one does is write a presentation for pi1 of the link complement, like the Verdinger presentation. And then you take each longitude Li as a word, mod pi n, which is the nth term of the lower central series, in preferred meridians. And this word is now showing up in the free group on M1 through Mn. Then one takes the Magnus expansion. So what this is a map. And this map is going to take our free group and map it to this ring on non-commuting variables x1 through xn. It'll send the ith meridian to 1 plus xi, and then it will send the inverse of that meridian to 1 minus xi plus xi squared, and so on and so forth. Then what you can do is define mu I, for indexing I, to be the coefficient of xi1 through xir minus 1 in the Magnus expansion of this word for the longitude LR. And you have to take it modulo the GCD of lower order Milnor invariants. So there's a bit of indeterminacy in here. Now this is just kind of a rough overview of Milnor's link invariants, the way Milnor defined them in the 50s. We're going to be looking at them through the knot polynomials. So before mentioning some places where the Milnor invariants show up, let's just look at the Brunnian rings for a quick example. Performing the Magnus expansion for, say, the third longitude would give you terms that look like this. And so from here you would be able to read off that mu1, 2 is mu1, 3, and that's mu2, 3. These are all the linking numbers of the components. These are all 0, and indeed they are for the Brunnian rings. All of the sublinks are unlinked. And then the triple linking number is going to be given by plus or minus 1 from these terms. So there are lots of different geometric interpretations of the Milnor invariants. They show up as Massey products in the cohomology of the link exterior. They can also be described via certain derivatives of the multivariable Alexander polynomial. This is due to Traldi, Murasugi, and Smith for the case of two-component links. And they can also be described as coefficients of the Conway polynomial. And you can find that in work of Cochrane. More work of Cochrane and Meller and Melvin shows that you can read these off as intersections of certain derived Seifert surfaces, which is how we were showing the Sauter-Levine invariant before. And these invariants show up in lots of different other places. They're significant to link concordance and string links, and even finite type and quantum invariants, and other topics that I'm less qualified to talk about. The interpretations that are going to be most important for this discussion are going to be as coefficients of the Conway polynomial, and to a lesser extent, their expression in terms of the multivariable Alexander polynomial that you see here. All right, so given that the Milnor invariants have all these different interpretations and seem to show up everywhere, it seems really natural to ask, can these invariants be located in the link Floer complex? Can the triple linking number be located in the link Floer complex? Now, this is a question to which the answer should obviously be yes, if you've thought a little bit about the link Floer complex and its Euler characteristic. But we're going to give an explicit answer to this question. And then the second question that I want to pose is whether the Milnor invariants place algebraic restrictions on the structure of link Floer complex. The first question is kind of a yes or no type question, but we would also like to have a more qualitative answer to that type of question. So let's talk a little bit about Heegaard Floer homology now. Heegaard Floer homology is due to Ojvath and Szabo, starting in about 2001 and going on today. And it has been worked on by many different people. It's a powerful package of 3 and 4 manifold invariants. And roughly speaking, what you do is you take Y. Y is usually a rational homology sphere, and you associate to Y a module. Now this module comes in different flavors, so I have a dot here, but this dot could be plus, it could be minus, it could be infinity. And in this case, you get an F adjoin U module, or it could be the hat flavor of Heegaard Floer homology, in which case you get an F vector space. This module splits as a direct sum over spin C structures, which I like to think of as being elements of second cohomology. And then each one of these summands itself splits as well. If we take, say, HF plus, then we can write this splitting like this. HF plus of y in spin C structure T has two summands. One of them is a free F adjoin U module, and the other one is a torsion submodule. So the torsion submodule is called HF red, and then the free part, there's only one free part, is usually referred to as the tower, and sometimes the notation math-cal-T will be used to denote the tower. Let's take a look at a couple of examples of Floer homology. So the first example is always the three-sphere. The three-sphere has Heegaard Floer homology that's just a single tower. We could also look at the lens space L31. L31 has no torsion, but it has three towers. And that makes sense because the first homology of L31 is Z mod 3, so you would expect that there would be three summands, one for each of the three spin C structures. And then let's take a look at one more example, the Brunnian sphere, sigma 237. So this has a single tower, and if it weren't for the torsion summand, we wouldn't really be able to tell it apart from S3. But there's a torsion piece, which we're writing as F. So right away, we can actually see something that I should observe, and that is what an L-space is. Let me jot down that definition. An L-space is a rational homology sphere that has the simplest possible Heegaard Floer homology. And what that means is that in every spin C structure, there is just a tower and there's no torsion. So in other words, the HF red piece should be 0. So we see here that we have two L-spaces that we're looking at. The sphere is an L-space, and then the lens space L31 is an L-space. And in fact, all lens spaces are L-spaces, which is part of the reason why they're called L-spaces. They generalize lens spaces. But this Brunnian sphere is not an L-space. The next fact that I want to observe is that Heegaard Floer homology has an absolute Q grading. This is actually much more than a fact. It's more like a deep theorem, but I'm just going to be saying it like it's a fact. And in the context of this example, we can put some gradings on everything. So for the three-sphere, the grading is going to be 0. And what I mean by that is that there's actually an entire tower here with one generator, x, and there's a U action. So this is, say, U inverse x, U inverse squared x, and the action of U takes us down the tower. The first element here is in grading 0. And then the grading of ux is equal to the grading of x minus 2. So that would mean the next element would be in grading 2, and then in grading 4, and going on and on up with the tower. So I'm just denoting the minimal grading on the tower. For the lens space, L31, each one of these towers has a minimal grading, which is going to be some rational number. And those work out to be 1/2, and then both of these are minus 1/6. Now, I'm not telling you how you get the grading for a lens space, but there's a recursive formula that exists that one could follow. And then the tower for the Brunnian sphere also has grading 0, like the tower for the three-sphere, but it has this additional torsion piece, which is also graded with a single grading of -1. Let's use these examples as an opportunity to make a definition that we're going to need later on as well. So D stands for d-invariant. And what the d-invariant of the three-manifold Y equipped with spin C structure T means is you take the minimal grading of the tower in that summand. So in the case of the three-sphere, the d-invariant is 0. In the case of the lens space, we have 3 different d-invariants, one for each summand, 1/2, -1/6, and -1/6. And in the case of the Brunnian sphere, sigma 237, the d-invariant is also 0. Note that the d-invariant does not distinguish S3 from the Brunnian sphere. You'd have to use the torsion summand for that. But this is what I'm going to mean by d-invariant. This is if you're using HF plus. If you're using HF minus, then you use the maximal grading of the tower in an analogous way. I'm going to be a bit sloppy and flip-flop between plus and minus at different times. Much like with the story for knots, if you have a link in S3 or in your 3-manifold, that link defines a filtration that gives additional structure and allows you to define link Floer homology. Our filtration is going to be denoted with an S, and S is going to be indexed by Z to the N for an algebraically split link. For the most part, I'm going to be looking at links of 2 or 3 components, so imagine that I'm being indexed by, say, Z2 or Z3. And my filtered subcomplexes are going to be denoted with A's. One of the most important properties of link Floer homology is that it categorifies the multivariable Alexander polynomial with a formula that looks like this. You take a certain normalization of the multivariable Alexander polynomial, and you can read that off as the Euler characteristic over S, the sum of the Euler characteristics over S. And this Euler characteristic is taken with respect to the absolute grading, the Maslov grading. And that gives you the coefficient, which then becomes the coefficient of the Alexander polynomial. Besides categorifying the Alexander polynomial, link Floer homology contains much more information about the link and about the 3 manifolds that are obtained by doing surgery on that link. Some of that information is captured by what's called the H function. This is a family of invariants that comes out of the gradings of link Floer homology. The H function is called different things when you're dealing with knots. It's originally due to Rasmussen. It also shows up in work of Ni and Wu, and the version for links is due to Borodzik and Gorsky. One definition of the H function is that if you've got your link in S3, then minus 2 times the H function at the relevant lattice point S, which is how we filter the link, well, that is the shifted d-invariant of a sufficiently large surgery in a certain spin C structure. In the work of Rasmussen, these numbers were called the local H invariants. And in Ni and Wu's work, these invariants, the analog for knots, are called V plus or H plus. If you take the H function as we've defined it and write it for knots, then what you ought to have is that HK of S, our H function, agrees with Ni and Wu's V plus in lattice point S, where S takes on a value in Z for the case of a knot. You can alternatively define the H function as the maximal homological degree of the free part of the homology of the subcomplex A. And what we actually work with is a normalized H function. And what we're going to do is we're going to be taking what we call little h. Little h of our link is defined to be the H function, but then we subtract off the H function of the unknot. And that's the version of the H function that we're going to work with for the most part, little h. Let's take a look at a quick H function example. What I have written out here is the H function of the Whitehead link. It's a bit mysterious where this comes from, but let's just take at face value that this is what the H function of the Whitehead link looks like. As it turns out, the H function for the unlink is going to look like the H function of the Whitehead link everywhere except at lattice point 0, 0. So this is going to be in purple. And so that would mean that here I would have a 0, but everywhere else it would look just like the H function for the Whitehead link. So that means now I can write down little h. So little h for the Whitehead link is going to look like 1 if I'm in lattice point 0, 0, and it's going to look like 0 otherwise. So it's much nicer to work with the little h function of the Whitehead link. It's compactly supported everywhere. It's equal to 0 except at 0, 0 where it's equal to 1, which is just easier to get a handle on. So there's some remarks that I want to make about the H function, and that is that it all lives in what's called the mapping cone formula. The mapping cone formula is this homological algebraic construction that tells you how to figure out the link Floer homology of surgery on your knot or on your link. The version for knots is due to Ojvath and Szabo in 2008, and the version for links is due to Ojvath and Manolescu in 2010. So here what you have is your knot, and associated to your knot is CFK infinity, the total knot Floer complex. I'm writing this for knots right here rather than links because notationally it's much more complicated for links. And this gives you some sort of bifiltered complex. Now this complex contains different subcomplexes and quotient complexes, and 2 of them are called A0 and A1. If you're more familiar with standard knot Floer homology terminology, then this would be A and this would be B. Now whether you call them A and B or A0 and A1, these sub and quotient complexes are quasi-isomorphic to, in the case of A0, large surgery along your knot. And in the case of A1, or what's called B, this is going to be quasi-isomorphic to the Floer complex of the manifold that you're sitting in, which for us is usually S3. Because of this, that means that these maps V, which go between them, and H, can be thought of as endomorphisms of the towers, these maps on homology. What this means is that this complex A has a known structure. It ought to look like large surgery, and there should be a single tower. And likewise, this complex A1, this also has a known structure. It should look like the Floer homology of S3, which also just has a tower. And so you look at the map that goes between these towers, and this is an endomorphism of an F adjoin U, a free F adjoin U module, which means it has to be multiplication by U to some power. So you go and you find what that power is. It's a non-negative integer, VI or HI, and this is how you define those numbers, V plus, which we were talking about before, or H plus. This is essentially how you define the H function in our language. There's a similar story for links, but I'm not going to try and write it down. Just keep in mind that it's analogous to the situation for knots. There's some more groundwork that I need to lay before we move on, and that is to talk about L-space links. L-space links are a little bit more complicated than L-space knots. We talked about what an L-space is. It's a three-manifold with the simplest possible Heegaard Floer homology, and what an L-space knot is a knot that has a positive surgery that gives you an L-space. So if you have some knot and you do surgery on it and you get the lens space L32, then you're going to have an L-space knot. Well, a link is said to be an L-space link if all sufficiently large surgeries are L-spaces. This is a little bit different than the situation for knots. It's well known that if you have a knot and you can do a single positive surgery and get an L-space, then you can increase that surgery coefficient, and the surgeries are going to continue to be L-spaces. But it doesn't quite work like that for links. You could have an isolated pair of surgery coefficients that you do on the two components of the link, and then increase one of those surgery coefficients, and then no longer have an L-space. So we need to talk a little bit more about what it means to be an L-space link. So if you do have an L-space link, and you know a priori that all of the large surgeries are going to remain L-spaces, then what you know is that those A- subcomplexes are torsion-free, and on homology, they just look like a free F adjoin U module. You also know that if you have an L-space link, that all of the sublinks, if you remove components of your link, those are also going to be L-space links. So you can't have a link whose component is a knot, which is known to be not an L-space knot, for example. The next fact is due to Yajing Liu, and these are conditions that basically tell us when L-space links work like L-space knots, in the sense that you can increase the surgery coefficients and you're still going to have L-space surgeries. So if you know that the sublinks are L-space links, and you know that the framing matrix is positive definite. What the framing matrix is, by the way, is if you're doing, say, surgery on a two-component link, then the surgery coefficients are the framings, so P1 and P2, and then the linking number of L1 and L2 would go here. So it's the linking number off the diagonal and the framings on the diagonal. If the framing matrix is positive definite and the sublinks are L-space links, then it works like the case for knots. If you have a single L-space surgery coefficient, meaning you take P1 and P2, and you do surgery and you get an L-space, then you can increase either or both of these. And all of those larger surgeries are still going to be L-spaces. And this is not too strong of a condition. For example, if your link is made out of unknots, then the sublinks are automatically going to be L-space links, or made out of, unknots and trefoils. And then checking whether the framing matrix is positive definite is pretty easy too. Okay, with a bit of groundwork laid, now we can pose and answer a question. Can the linking number be located in the link Floer complex? Yes. Let's see how that works. The first thing to remember as we work through this is that link Floer homology categorifies the multivariable Alexander polynomial. So more specifically, what we want to do is take the multivariable Alexander polynomial and we want to factor out a t to the 1/2 and a t2 to the 1/2. That's what we mean by delta twiddle. And link Floer homology categorifies it in the following way. This is the formula that we saw before. We're summing over S1 and S2, which are in Z2, and we're taking the Euler characteristic with respect to the Maslov grading in each one of these lattice points. That gives us the coefficient of the multivariable Alexander polynomial. Now, the nice thing about L-space links is that if you don't have any torsion, then you can write this Euler characteristic in terms of just the h function. Now, if you do have torsion, you have to write down a more complicated formula. So I'm going to explain how linking number works in the case of L-space links. You can do it more generally, it just looks really messy. What that formula in terms of the h function looks like is this. Everything is controlled by the tower because there's no torsion. So you really only have to consider the maximal degree of that tower. We're working in minus now, so it's a maximal degree rather than a minimal degree. And this formula is essentially following from the inclusion and exclusion formula applied to the multifiltration. The next piece of information that you want to remember is that the linking number, which by the way is the Milnor invariant mu12, can be read as the first coefficient of the Conway polynomial. If you're writing down your Conway polynomial, that's going to look something like a z factored out of an expression that looks like a0 plus a2z squared plus a4z to the 4th, and so on. And this a0 is your first coefficient of this Conway polynomial, and that is the linking number. The last thing to do is put all these observations together, and then when you do that, you can see that the linking number of your two-component link is the normalized Conway polynomial. Normalized here means I'm dividing out by z. I'm normalizing it, and then I'm plugging in z is equal to 0. That gives me the coefficient a0. By the change of variables that goes from Conway polynomial to Alexander polynomial or vice versa, this is the same thing as evaluating the normalized multivariable Alexander polynomial at 1. But when I'm doing this, that means I am also using this quantity. I'm taking the sum over the lattice points S in S1 and S2 of the sum of the little h function. Now there's a little bit of sleight of hand here. I'm replacing capital H with lowercase h. Using these sums is going to give me the same quantity, but I want something which is finitely supported, and so I'm going to be switching to little h. But this is essentially how it works. All right, now that we've worked it out for linking number, we can also work it out in a similar way for the Sodel-Levine invariant. Remember that the Sodel-Levine invariant is the Milnor invariant 1, 1, 2, 2. The strategy for finding the Sodel-Levine invariant is going to be much like the strategy for finding the linking number, just with a few more details. So when the linking number is 0 for a two-component link, then the next coefficient of the Conway polynomial is your Sodel-Levine invariant. So this is going to be a2 in our Conway polynomial. Let's look at the multivariable Alexander polynomial now. If we're going to be factoring out a z squared from our normalized Conway polynomial, then we're going to be factoring out a t1 minus 1 and a t2 minus 1 from our normalized Alexander polynomial. And this follows from the Torres condition. The Torres condition is a statement about how the Alexander polynomial of a sublink relates to the Alexander polynomial of the entire link. So from this equation, we see that the coefficients of the Alexander polynomial are related to the following sum of coefficients. And you use a little bit of pattern recognition and see that this is starting to look like the pattern that we saw with the h function from before. So you have to use some careful bookkeeping, and you have to convince yourself that the coefficients of the multivariable Alexander polynomial are related to sums of coefficients not quite of the h function, but of something we call h prime. And what h prime really is a state sum formula for the h function taken over the sublinks. What you produce is a formula that looks like the Sodel-Levine invariant as the sum of h prime. And we're looking at two-component links here, only two-component links. And so what h prime looks like is going to be the h function minus the h function of the first link component minus the h function of the second link component. If you have more link components, then h prime will be an alternating sum taken over the sublinks of the link. But here we just have a two-component link. And so that's how you find the Soto-Levine invariant. I should also mention that if you would like to get rid of the L-space link assumption, you can certainly do that and write down a formula for the Soto-Levine invariant. You'll just need to take into account the Euler characteristic of the torsion sumends of link Floer homology, and writing that down just looks somewhat messier, so I've omitted it from the discussion today. Finally, we ask, can the triple linking number be located in the link Floer complex? Of course now the answer is yes. Let's look at the theorem statement for this one. As before, we are going to need to work with the multivariable Alexander polynomial and the Euler characteristic. So we have our algebraically split link, and we have a little lemma that says you can write that in terms of the h prime function and what we call the chi prime function. Now, what h prime is like what we were discussing before, a state sum for the h function over the sublinks, and that's what I have written here. I'm summing over index sets I, and these index sets are going to describe for me sublinks of my link. And then given my index set for my sublink, I'm going to take the h function for that sublink. And it's an alternating sum. So this forms my state sum for h prime, and I have a similar kind of state sum in terms of the Euler characteristic of the torsion sumends. When you're dealing with an L-space link, then you don't have chi prime at all because you have no torsion, and so you just have this alternating sum over the h functions of the sublinks. But in general, you're going to need to have this other piece as well. And something important to note here is that these functions have compact support. One of the nice features of this little h function is that it'll have compact support, and the torsion pieces are also going to have compact support here. So having written down h prime and Euler characteristic prime, we can now make the general statement. If L is an algebraically split link with three components, then the square of the triple linking number is up to sign the sum over S of h prime minus chi prime. And in particular, this tells us that this quantity is a link homotopy invariant for three component links. The formula can be simplified a great deal if you consider L-space links and if you consider links that are Brunnian, or both. So a Brunnian link means that the sublinks are trivial, kind of like the Borromean rings. If L is a three-component Brunnian L-space link, then the square of the triple linking number is just the sum of the h function, not even h prime, just the plain h function. This is as simple as the formula gets. And moreover, if the triple linking number is 0, then L has to be the unlink, and it can't ever be equal to plus or minus 2. So the formula becomes very nice in these cases. We now have a fairly decent understanding of how to read off the triple linking number, or the Soto-Levine invariant, from the link Floer complex. So I'd like to bring it back to the more qualitative question. Do the Milnor invariants place algebraic restrictions on the link Floer complex, and what does that mean? So we're going to be taking a closer look at this question, and we're going to be comparing the Milnor invariants to the d-invariants of surgery on these links. Let's say we have our algebraically split link L, and we assume that all two-component sublinks are Q L-space links. If the triple linking number is non-zero, then the d-invariant is bounded away from 0. In particular, the d-invariant of 1, 1, 1 surgery is less than or equal to minus 2. Also, if the triple linking number is odd, we can make an analogous statement with Z2 coefficients. So there's various things that I want to discuss about the theorem statement and some remarks to make. And the first one is about coefficients. So you'll notice here that I've said Q L-space links. We want to assume that our sublinks are L-space links. Now, I didn't say anything about coefficients before, but I was working under a blanket assumption that everything was with Z2 coefficients. This is a standard assumption that people make in Heegaard Floer homology because nobody wants to work with signs. And everything I said before holds over Z2. But from this point on, we're going to be working with Q coefficients. And the reason for that is because we need to make a comparison between Heegaard Floer homology and monopole Floer homology in order to prove the theorem. So from here on out, we have to use Q coefficients. So when I say Q L-space link, what I mean is now we're doing everything over Q, and I still mean an analogous definition of an L-space. So it has the simplest possible Heegaard Floer homology in the sense that there's no torsion as a Q adjoin U module. Well, Z2 L-space links and Q L-space links are actually the same, but what we don't know for sure is whether the d-invariants defined over Q agree with the d-invariants defined over Z mod 2Z. So for this reason, we have to be really careful with coefficients. And this is the type of statement that we want to show. Some more remarks about this, and that's that this L-space link condition at all is necessary. In our article, we have some counterexamples that explain why. And what we can do is do a Bing doubling trick to show that you can have the triple linking be 1 and the d-invariant be 0 if you do this. So this result is established using surgery triangles, and it's roughly something that looks like this. We have a 3-component link, and we'll be doing either all 0 surgery, 0, 0, and then infinity surgery, or 0, 0, and then large surgery. And then the comparison to monopole Floer homology that we need to make is because Kronheimer and Rovka have a theorem that says if the triple linking number is non-zero, then the monopole Floer homology of 0 surgery is rank 6, which is a piece of information that we need to use in the surgery triangle arguments that we want to make. Now this theorem is fairly technical, so I'm not going to go into the proof, but this is some of the information about what goes into it. So what is the significance of having a bound like this? Well, now we can say that if the triple linking number is non-vanishing, then the manifold that you get by doing 1-1-1 surgery has infinite order in the homology cobordism group. And a related statement is that it doesn't bound any rational homology ball. So that's a nice kind of topological statement that we can get from this, that we relate to triple linking now. If you like to consider cosmetic surgery problems, and that means when you're doing a surgery that starts in a manifold Y and then ends up in the same manifold Y, that would be considered a cosmetic surgery, then you can say something like this. Any 3-component Brunnian link with an all +1 cosmetic surgery has to have triple linking number equal to 0. So these are just a couple of quick corollaries that you get out of a bound like what we have. Along with this bound, we prove a small collection of detection statements that I'm going to run through quickly. One of the things that we do is we have detection for Brunnian L-space links. And there's a lot of things to say here, but if your link has 2 components and the Soto-Levine invariant is 1, it'll have to be the Whitehead link. If your link has 3 components and the triple linking number is plus or minus 1, it has to be the Borromean rings. This is all under the assumption of being Brunnian in L-space, by the way. And if your link has greater than or equal to 4 components, then it has to be the 4-component unlink. These are essentially the only kinds of Brunnian L-space links, or at least the only Brunnian L-space links that have Soto-Levine or triple linking number equal to 1. Let me go over a sketch of this. We want to show that if we have, say, a 2-component Brunnian L-space link and the Soto-Levine invariant is 1, then L is the Whitehead link. By Brunnian, for a 2-component link, what I mean is that each one of these components, L1 and L2, are unknots. Imagine the Whitehead link. But we want to show that it actually is the Whitehead link. Since the Soto-Levine invariant is equal to 1, and we know from our formulas that this is the sum of the h function, not even h prime, but just the regular h function, then by the properties of the h function, we can pinpoint exactly what it is. It's going to be 1 when S1 and S2 are both 0, and it's going to be 0 otherwise. If you remember from our example before, this is actually the little h function of the Whitehead link. From here, we want to argue that this is enough information to actually pin it down as the Whitehead link itself. For that, what we do is we look at the link surgery complex. And now we know that the d-invariant of 1-1 surgery on this link is minus 2h by definition, and we know what this h is. So this tells us that 1-1 surgery is an L-space and it has d-invariant equal to minus 2. This sounds a lot like the Poincare homology sphere because it is the Poincare homology sphere. The image L2 prime of L2, the second link component, is a genus 1 L-space knot, and that means that L2 prime has to be the trefoil. And 1 surgery on the trefoil is the Poincare homology sphere, and that is equal to 1-1 surgery on our link L. What we have now is an argument that says that 1-1 surgery is the Poincare homology sphere, but we haven't quite pinned down the link as the Whitehead link. But this will follow after we prove our next detection statement. Our next theorem says that if you have an L-component Brunnian link and you're doing 1-1-1 surgery on it, or 1 over mi, and it's the Poincare homology sphere, then if you're in the 2-component case, then L was actually the Whitehead link, or its mirror. And there's some other statements for the 3 and 4 and higher cases as well. So next we have to prove this. So what does this follow from? Bear in mind here we're looking at the 2-component case as we go along, but there's going to be analogous statements for the 3-component case. Well, when you have a 2-component Brunnian link and you're doing 1-1 surgery on it and getting the Poincare homology sphere, it has to be the Whitehead link. And you convince yourself of this by first looking at the image of one component in N surgery on the other. What you've got is a genus 1 fibered knot in a lens space. And the fact that it's genus 1 in fiber follows from work of me. Baker has a classification of genus 1 fibered knots in lens spaces, which we use here. And L' agrees with N surgery on one of the components of the Whitehead link for most values of N. And what this means is that the exteriors of L' and the image of the Whitehead link under this surgery on one component agree for infinitely many N. And so the exterior of your link looks like the exterior of the Whitehead link. And finally, we argue that the link actually is the Whitehead link, using our assumption that one surgery gave us the Poincare homology sphere. There are more detection type results that we prove. We prove a result that says if you have an algebraically split L-space link, that's the Poincare homology sphere, then L is either the Whitehead link or the split union of the trefoil and the unknot. In some of the statements, we assume that we have a Brunnian link, and some of the statements we don't, like this one. So these are the types of statements that we can make and prove. You can find this work, by the way, posted to the archive now, and it's been submitted. So I'd like to close by posing a couple more related questions. First, can we find other Milnor invariants in the link-Floer complex? The Sodal-Levene invariant and the triple linking number are not the only high-order linking numbers out there, so what about the other ones, particularly if we take links that have many components? And then a related question is, are there Milnor invariants that we cannot find in the link-Floer complex, and how would we go about doing that? Another question that I personally have is how to understand Cochrane's derived linking numbers in terms of link-Floer homology. Cochrane's derived linking numbers are a manifestation of some of the Milnor invariants in terms of intersection theory. They're intersection numbers of certain surfaces that he gets in a derived way that I won't explain. I think it would be nice to have a more concrete understanding of these surfaces in a way that doesn't necessarily go through knot polynomials. And there are no doubt lots of other questions that one can ask about higher order linking and link-Floer homology. It's a pretty open area, so I encourage everybody to think about it. So thank you so much to the organizers for asking me to put this together. I hope that I have a chance to meet you all in person and to talk about this in the near future. Bye-bye.